All right. Okay, so we talked about in the last presentation that one of the things that Polkadot provides, one of the most important things that Polkadot provides, is shared security for all the parachains. So this is a non-technical approach to explaining at the high level what shared security is, and then I'll pass it over to the parachain team engineers like that to actually explain how it all works at a more low level, right? But what I really want to get into your head is the mechanics of what is happening during shared security, right? And so that you can understand kind of at a mechanics level how Polkadot is actually able to scale. The goal here is that at the end of this presentation, I would truly hope that you could explain to to someone who doesn't know blockchain but understands general high-level engineering how Polkadot scaling works. It should be able that you could draw on a paper and actually get the same kind of idea passed, okay? So, what is shared security? On the surface, shared security is an economic scaling solution for blockchains, right? It makes sense that basically you have a bunch of chains, we have a multi-chain future, you want them to all be secure, right? If they're not secure, they are attackable, and then the properties of blockchains are not useful. So it is an economic scaling solution. But that's just an answer that sits at the surface, and the topic goes much, much deeper than that. So let's explore what is security and what is shared security, right? Oh, what did I just do? Resume. Okay, what is security? Nearly every attack to a blockchain falls into one of these two buckets. Technical security, like the cryptography, the actual code of your blockchain, and economic security, the game theory plus economics. We're going to focus on economic security. This technical security we've been learning through Substrate and Polkadot and the game and the cryptography sections, all that kind of stuff, right? But really, when we're talking about shared security, we're talking about scaling economic security, okay? Economic security is represented by the economic cost to change the canonical history of a blockchain. Change with higher security or more resilient to malicious activity like a double spend attack. So there is always the ability to fork chains and create differences. Economic security is about how much does it cost if you wanted to maliciously fork a chain and cause some problems at that level. That is what economic security is. How much does it cost to do this kind of attack? I want to note that a double spend is not inherently an attack. Actually, if you remember, the whole point of blockchains is to come to consensus about a double spend. A double spend is a perfectly valid operation on any blockchain. A double spend being that I have some tokens and I do two transactions at the same time to two different users. It is the point of a blockchain to come to consensus about that activity, right? So double spend is not inherently an attack. It is up to the blockchain to figure out which of the two blockchains are the valid ones. The double spend attack, though, happens, like, what is an actual attack like? It happens something like this. So imagine in this example that someone is trying to take advantage of a fragmentation in the network and try to create two different canonical chains. So in this context, and sorry, no offense to any Australians, Australia is trying to attack the world, okay? And you basically have 33 honest nodes in all of the Asia-Africa region. You have 33 honest nodes in all of the Americas, and you have 33 malicious nodes in Australia. And the pipeline between the internet is that all internet activity passes through Australia, whatever, right? There's a fragmentation in the network across the Americas and Asia, Africa, okay? Again, no offense to Australians. What happens? So you basically have, here these malicious nodes going and creating two different blockchain histories, which the Americas thinks is valid and which the Asia Africa thinks is valid. And actually, in this context, for this attack to really work, it needs to be 34, right? You need a slight majority. But basically, in this circle of red blockchain, you have more than 66%. And in this circle of blue blockchain, you have more than 66%. But they're being malicious because they're actually validating two different histories of the blockchain. This is an attack. So what happens after the attack? So after some time, activity, the fragmentation goes away, and you actually have the two honest regions talking to each other. And they realize that Australia has been lying to them the whole time. They realize there was actually an attack happening, right? And they're actually able to prove the malicious nodes equivocated. And what does that actually mean? Equivocation here meaning that the malicious nodes signed blocks which contradict each other, right? They sign that Alice sent to here and that Alice sent to here. And if they were good nodes, they would never sign both messages. These would be contradictory states. But because they signed the messages, we are able to show that they equivocated. And again, what do we know about signing? We learned this in cryptography. When you sign a message, you cannot redact the fact that you signed it. The signature is the proof that you actually did some action, right? These are important properties, again, tying all the way back to cryptography. So they cannot deny that they did this action. So what is the economic cost of this attack? The economic cost of this attack, knowing that they equivocated, means that they will get slashed. Our blockchain logic has it such that if we detect two conflicting signatures, or that's reported to the blockchain, we will slash those nodes, right? And the slash should be economically large enough to deter the kinds of malicious activities from occurring. So I want to clarify, I didn't mention here how much they get slashed. That is actually configurable for you as a blockchain developer. But you need to ensure that your slashing mechanism is high enough such that these attacks are not economically viable. Yes, one more time slowly. So, because we have now evidence of this malicious nodes signing two different blockchains, and this is proof, we can submit this proof to the blockchain. We can have logic of the blockchain which ingests this proof and says, oh, you're right. These two are equivocated, right? They're lies. We can actually create logic on the blockchain which will then slash those nodes, which will take their money away. The economic cost in this context of attacking Polkadot is getting slashed. And again, without picking a specific number, we need to, in general, pick a number where that the slashing mechanism is large enough such that this malicious activity is deterred from occurring, right? Does that make sense? Is that okay? So in this context, economics and security are tightly coupled in blockchains, right? The economics of being able to do this attack is directly tied to the security of that network. Okay, so let's talk about the bootstrapping problem. What is the bootstrapping problem? The bootstrapping problem is basically the struggle that new chains face to keep their chain secure when their token economics is not yet sufficient or stable, right? In many ways, the scarcest resource in blockchains is economic security. It's not computers. It's not actually computer scalability or that kind of execution scalability. It is actually economic scalability. There's simply not enough money to go around. New chains usually have small market cap. New chains are usually more speculative. This means inherently these chains struggle to actually provide the economics required to secure themselves from an attack. Again, this is the tie of these two things. That you can have all the same code as Polkadot, right? All the same logic. But if you don't have the economics to actually punish bad actors enough, they will do attacks because somehow it is more economically incentivized for them to make that attack. Imagine that they have some arbitrage on some other network or some exchange that will, when the token dumps, that they'll make a bunch of money, right? If your chain isn't secure enough, then you cannot prevent these kinds of attacks. It's not a technology problem, it's an economics problem. So how do we solve this problem? Shared security. That if we can know this problem in advance and we can prepare for a future for multiple blockchains, and we know that this is an issue we need to solve, we need to create a technology. And that technology in Polkadot, shared security. We've had it since the white paper. There are other chains now just catching up to this idea today. There's many jokes that like the other protocols 2.0 is Polkadot 1.0. And we're building Polkadot 2.0. So what does that mean, right? That's the shill. Okay, anyway, back to the content. Different forms of shared security today. So there are different forms of it. We have native shared security. This is implemented at the protocol level and is represented as a layer 0 blockchain working underneath layer 1 chains. This sounds very familiar, right? Rollups, you have optimistics and zero knowledge rollups, which use a settlement layer to provide security and finality to the transaction. So really, rollups are a form of shared security, but kind of after the fact. And then restaking. There are some protocols that allow the use of already staked tokens to secure other networks, usually through the creation of derivative tokens. But these different forms are not equal. Okay, they are not the same level of shared security. They're different technologies. So what I want to do is, I am not an expert in restaking. I am not an expert in rollups. I want to present to you Polkadot shared security, allow you to have an understanding of it, and then be able to approach other technologies with this knowledge in mind, and you can make for yourself the decisions and trade-offs. Again, everything is a decision, right? And I have some slides at the end which describe at a high level what I understand about the pros and cons of each of these different protocols, okay? But I want to give you concrete knowledge of exactly how Polkadot shared security works, native shared security. So Polkadot is unique in that it provides all connected parachains with the same security guarantees as the relay chain. This is native to the protocol and one of its core functionalities. Polkadot prioritizes, beyond even making transactions and transfers happen, that parachains are secured. That is the core level functionality of the Polkadot relay chain. So what are the building blocks of shared security? So this is what I want to walk through. First is an execution meta protocol. To make shared security work, we need to provide an execution meta protocol. We need to then have a coordination validation logic, and finally a security hub or settlement layer. And what this actually looks like on Polkadot is WASM, maybe RISC-V in the future, the parachains protocol itself, and then the relay chain. So let's walk through those different aspects. First, WASM. Again, you cannot overemphasize the importance of WASM. In the ecosystem, in the Polkadot ecosystem, each chain has their state transition function, their logic, their being written into WASM, represented by WASM blob, and that is stored on the blockchain itself. This has many implications. We've covered that throughout the entire lecture, technical side, the design side. But in terms of shared security, the key context here that it is very easy to share a generic, safe to execute WASM blob and to actually execute it itself. This is the main idea. And we have an analogy. There's a game console analogy. I think we've seen this once before in Substrate, right? Let me re-emphasize it here. You can really think of Substrate clients, and in this context, Polkadot clients, as just like a game console. It is a generic execution environment for a well-formed game. And you can imagine that your Substrate client doesn't have an identity. But when you plug in the Akala cartridge, when you plug in the Moonbeam cartridge, when you plug in the Polkadot cartridge, it becomes a fully running environment that you can actually interact and play with, right? So this is what we're talking about. WASM very much is a tool to define cartridges, games for our game console. And so Polkadot is the next level of that. Polkadot is not only that, but that for all different blockchains at once. That Polkadot is a Substrate client, but has in it the WASM of all the different parachains, so that you can actually execute all the different blockchains sometimes at once in the Polkadot environment. This is what we're designing here. This is really the high level idea of a Polkadot validator node. Okay? And again, this comes from the fact that we have WASM, a shared standard for executing logic. So in short, as you have all learned, the Polkadot client is basically a WASM executor. All of the chains in our ecosystem use WASM for their state transition function. The WASM meta protocol allows Polkadot to execute any chain on the fly. You give me the WASM, I can execute your chain. And note that we actually execute the blocks of the other chains. We actually execute. We're not doing some kind of optimistic rollup. We're not doing some kind of trust system, some kind of third party, whatever, some kind of, what is it called? What is it called when you want to say something is bad? There's a period where you can, a challenge period. We're not doing this challenge period stuff. We are actually executing the chains. It's less trust, more truth. The philosophies. Oh, that's wait. Yeah, actually, let's go. This is a great time for a question. Can we get a cube right here?
Can you go back one slide?
One slide.
So basically, like the WASM meta protocol, is that like constructed by those kind of primitive palettes we have in Frame? Is that even related?
No, remember, all of those palettes, you're compiled. It's Rust code. You're building a Rust thing. All of that gets compiled to WASM.
I know, but I'm saying, like, you're saying the WASM meta protocol. Is that like something?
No, it is WASM. WASM is the meta protocol.
Okay.
So the fact that we compile to WASM means now we have a blob, which is a WASM blob, and this can be executed in a WASM environment. And your browser can be a WASM environment, the node can be a WASM environment, etc. Like, you don't have to download, for example, like if you were to run a native chain on your Windows computer, you need a Windows binary. On your Mac computer, you need a Mac binary. On your Linux computer, you need a Linux binary. You need a separate binary for each of these. And for each chain, you would need a separate binary, and you need for all of those environments, run it. In this context, I can make a single execution thing, like a WASM executor for Mac, and then I can just hand you a WASM and you can run it right away. That's the whole idea.
But the concept of the shared security, like those concepts that
we're still building to that. Maybe then just let's pause for on that. Any other questions about WASM specifically? because I'll build more to the ideas. Let's keep going then. So then, first aspect, a shared execution environment. Next aspect, parachain validation, logic for verifying things are happening. So we want to maximize scaling. A scalable proof of stake system is one where security is as shared as possible and that execution is as sharded as possible, right? We want to share pool all the security into one. The more security we can bring together, the better for everyone. But we want to execute things in the most sharded, parallelized way as possible. Okay? Execution sharding. It is the process of distributing blockchain execution responsibilities across a validator set. In Polkadot, all validators execute every relay chain block, but only a subset execute each parachain block. This enables Polkadot to scale. So in this context, all the nodes, all the validators of Polkadot, they share the economics of the DOT token. They share the security of that economic backing. But they shard the execution of the individual parachains. This enables Polkadot to scale. So how do you validate a block? This goes back to our question. What are the building blocks needed to do a basic validation? Well, first, we need a block of transactions. This is the state transitions we want to execute in our state transition function. We need a block of transactions. We need state on which to execute those transition functions. And then we need the state transition function itself, which will then transition that state to a new state, right? That's the basics. But I want to note here, we don't need all the state of the whole blockchain, right? We only need the relevant state for these transactions. So in your blockchain, if you had 1 million users, but this block only has a transfer from Alice to Bob, I don't need to know the balance of your 1 million users. I need to know the balance of Alice, the balance of Bob, in a Merkle proof, taking advantage of the properties of Merkle trees, and I'm able to execute the logic on just those two pieces of data and create a new Merkle proof because all the other nodes are unchanged that are exactly equal to the data you would have if you had all the data, right? Does that make sense? One more time. I'll say it one more time. You have a set of transactions. These transactions do not necessarily act on all the data on your blockchain. It only acts on a subset of data. And in order to safely, securely, and verifiably execute that transaction into your state transition function, you do not need all the data. You only need the data which is relevant for this transactions, right? And using the property of Merkle trees, we are able to construct a full new Merkle tree subset where all the pieces match as if you had all the data. It is basically a light client proof. Okay, we have a question in the back. Can we bring the mic?
So I remember the class of where you was explaining the Parity DB. And in this case, the node who are executing this, they have the data of all the parachains, but in that context, when they will execute, they only like assemble the path to get through the specific data.
So no. So if all the validators had all the data of all the parachains, that would not scale. That would not be data sharding. Instead, what happens is the parachains themselves, they are responsible for holding their data, right? That's their own set of nodes, and they provide proofs, these POV blocks, to the relay chain in memory, and then the relay chain can then verify all the data. So you have your whole database, everything. I don't want it. Me holding your data would not let me scale. But you can provide to me, like in memory, the high-level version of the data I need to execute your block, and then I can validate it.
So each parachain has their own overlays.
Each parachain has their own set of nodes, which we call collators, which hold their data. So like if you want a block explorer on your parachain, Polkadot doesn't provide that. You have to provide that with your node network.
Okay.
But what we can do is we can scale the validation process of that your chain doesn't have to be secure, because we will secure your chain by validating every state transition function. You have one more question in the front. Can we get a mic?
Luca.
That means that on the relay chain you just store the Merkle root, right? Okay. But what happens if the collators or the parachain just go offline and that you don't have any data availability?
Great question. Let's keep going. Let's keep going. Okay. So we agree. This is the minimum requirement to validate a block. We all agree. So let's actually look at that process. So knowing this, what we can actually have is we have the relay chain, and we actually have parachains running on their own outside of the relay chain, and they can submit new blocks of transactions with their proof of validity to the network. And what Polkadot stores is two things. We store the WASM runtime for all the parachains. So actually, you go to Polkadot, you'll actually see the WASM blob for every parachain. And we store the Merkle root, right? Just what you said, that Merkle root, which allows us to verify that this proof actually matches the latest state, right? Just a single hash, very lightweight. We ingest that data, and now the relay chain has the WASM runtime, the block of transactions, and the POV, which match the Merkle root. And now we have a bunch of validators. And the goal is, how do we get these validators to do their job? What we do is we randomly assign validators in our validator pool to the different parachains, and only that subset will actually validate those parachains, right? And then they execute the block, and the new state root is committed to the relay chain, right? So we actually execute the state transition function, we get a new state root, and now this is the thing we store for the next time this process happens again. So here you can see how we're sharding execution and sharding data. So how do we stop things from going wrong, right? This is the question, basically. And there's big blocks. You will learn about all of these processes much more in detail tomorrow. But the idea is we have data availability. We use erasure encoding across the validators assigned to the parachains to make sure data needed to validate a block is always available in the validation time. So we have our own data availability network built into Polkadot. We have approval checking, that every validator node is running an approval checking process for a random subset of parachain blocks in every relay chain block. If the initially assigned approvers for a parablock is a no-show, they don't show up, then we assume an attack and the worst case escalate to have the entire validator set check the block. So basically, we have a mechanism that we give it to a subset, we hope they do the process. But if something is going wrong, we then escalate the process so that all the validators will actually try this block and actually figure out what's going on, you know? Finally, we have dispute handling. In the case where someone is trying to cheat the system, where someone is trying to be a malicious node, you can have someone dispute the validity of a parablock, and all the validators then go and say, hey, I will actually verify for myself, is this thing valid or not? And then come to a conclusion, right? So we have the sharding. In some ways, you can think that, okay, well, these guys are doing their job well, but anyone can go and say they're doing something wrong, and everyone has the ability to go stop what they're doing, but basically go and then validate for themselves, is this real? Less trust, more truth. We actually have a whole mechanism built in to be able to validate that all of these things for themselves are happening, right? And in the best case scenario, we have very nice scalability properties.
Those are the validators of the relay chain. So that means that every validator has a piece of every parachain, and they need K out of N to reconstruct the data of that parachain.
So the data being stored in data availability is not all the parachain stuff. It's just the POV. So the parachain is submitting to the network that subset of data it needs, and then that stuff is being erasure encoded. So it's not like we can reconstruct all parachains from the relay chains. That is not scalable. That's not great. We only need to construct the data needed for this execution. So we are only erasure coding this block of transactions and the POV stuff. We're distributing that.
And
Am I wrong? You want to speak?
but it's only for 24 hours, so it's a very temporary storage of this data needed
Right.
for validation.
It's only for 24 hours because it should finalize in like 6 seconds, like on average, right? 12 seconds. Store their own data. This is scalable. This is the scalability. It's secure because, okay, so this is great. If Polkadot had all the data of all the parachains, it is literally not scalable. It is literally the opposite of data sharding. So how is it secure? We use the property of Merkle trees and the fact that you cannot generate a Merkle hash with data which doesn't, it doesn't match, right? Like, okay. If the parachain is only shooting itself in the foot, right? If the parachain doesn't want to provide the data, then it is only hurting itself. It's not hurting anyone else in the network. I mean, it's like, again, who is the attacker? The parachain itself is the attacker. And again, parachains themselves can be different levels of centralized. Like you can have a private blockchain running on Polkadot, but in general, if you're building a public protocol, anyone could be a collator for that network, right? So again, if I don't provide the data to Polkadot, I'm not going to make your block. I mean, that's your choice. That's your problem. It doesn't hurt any other thing. Yeah, question.
So what does the block in Polkadot or the relay chain have exactly then? Like in each block, what is the transaction in this case? Because there are multiple.
There are parachain pallets, and in the block we are accepting. I mean, I'm going to say words here that are maybe not. We didn't go over that much, but we are accepting inherent data. Inherent data is basically like this data that's coming from the block author, and he is pooling this information that's happening like all in the network, and he is putting these parachain blocks into the relay chain block through inherence, and then that stuff is getting minted, right? Like,
So the short story is we have something called a candidate receipt, where candidate is this para block, and candidate receipt has a Merkle root of the new state. It doesn't have transactions. It only commits to the transaction, but it doesn't store them. So a hash again, and it also has hashes of all the XCM messages that might be a bit you might be unclear what it is. It will be clear later on. So we don't have any actual information you can immediately understand, but if someone would provide you the data, provide you the messages, you can confirm that they were actually included in that relay chain block. It will be, again, tomorrow, very in detail, everything will be listed and explained.
Let's say more high level, okay? More high level. Questions will be answered. But at a high level, hopefully this makes sense, right? At a high level, okay?
So on high level, we each block in the relay chain will have the Merkle roots, all the Merkle roots for all the parachains at this block. Is this correct?
Exactly. We can actually go into storage. You can go into the Polkadot.js API. You can go to the parachains palette. You can go into the blockchain thing, and you'll see the Merkle root for that chain.
Thank you. But then is there also like a state root for the relay chain?
Yes, that's a whole, like, the Polkadot is also a blockchain itself. So it's holding data, like the necessary data needed for each of the parachain blockchains, but Polkadot is its own blockchain. So it has its own system palette and its own.
But it's derived, like the root of the parachain is derived from the roots of the the root of the relay chain is derived from the roots of the parachains plus the
Exactly, because the root of the parachains is in the block, is in the relay chain storage. So it's part of that root, right? It's like roots of roots, right? Yes. The answer is yes. The answer is yes. Okay, let's keep going. So we talked about two pieces. We talked about WASM, the generalized execution format. We talked about a protocol that makes sense to actually validate blocks, and then, if things go wrong. The last piece is the relay chain, right? The relay chain. The relay chain is really the security hub for Polkadot, right? And this security hub thing is a whole new narrative, right? But really it is the security hub for Polkadot. It is an anchor point for the whole network. It provides a base economic utility token with DOT, right? It provides a group of high quality validators for this process. It stores essential data needed for each parachain and the process. It establishes finality for the parachain blocks. So the relay chain has these purposes. It is giving the DOT token, which is security. It is giving the validators through this economic staking system. It is giving it is a blockchain itself, so it can store data in a verifiable, immutable way, and establishes finality. It has its own finality consensus so that it can provide finality to all the other parachains. It is a security hub. And so the idea of parachain block finalization. So the relay chain block producers commit the new state root for the relay chain once parachain protocol has been completed. Thus, when a relay chain block is finalized, this is what these white ones are, they're the finalized ones, all included parachain blocks, the colors, will also be finalized, right? Finalization does not come from the parachain. Parachains themselves have no control over their finalization. Finalization for a parachain is that your block has been included in a finalized block of the relay chain. The parachain state committed on Polkadot is the canonical chain. Your canonical parachain, when you do this process, you're giving it up to Polkadot to decide what canonicality is. Yeah, okay, that word. I can type it for you if you want. But what is canonical, right? So that is the main idea, okay? Canonicality. Okay. Trust-free interaction. Then again, as I mentioned already, that this finalization of all the parachain blocks along with the relay chain also allows for a security and finalization of the interactions, right? So as he mentioned, there's these XCM messages that are also being passed in as a part of this process that we are actually able to finalize the interaction between two parachains. Unlike a bridge where you have two separate chains with their own consensus, with their own finality, and some kind of soft bridge connecting them, if one of these chains rolls back finality or rolls back consensus, then you leave the other chain stranded. You leave them kind of fucked, right? That we actually don't allow these bridges to be a third-party actor. They are a first-party actor in our system. That parachains and the way that they interact are finalized along with the relay chain block. All of it happens. This is security for interactions as well. Was there a comment? Can you get the mic? Sorry. Get this behind you. There's one here too. Okay, well.
So there are two finalizations, one in the parachain.
No. There's one finalization. The only finalization is the relay chain. So
Grandpa is running in the parachain as well. So among their own validated nodes.
no, they do not have they have some soft consensus. They have the like block production, the Babe aspect. So again, this goes back to the split. We split Babe. So the parachains are running Babe. They're running some process to be able to execute and figure out where to build blocks on.
Yeah.
But they have no finalization. The finalization, all of Grandpa is only on the relay chain.
And it trickles down to parachains. So once the relay chain is finalized, then it trickles down to the specific parachain blocks that are inside of that relay chain block, and they are finalized as well.
Nice. Okay, cool. Again, you'll learn more about the details from him, who knows much more than I do. I'm just good at the big picture. Okay, so anyway, so let's go back. The building blocks of shared security. So I showed you now these pieces, right? You have an execution meta protocol, you have a coordination validation process, you have a security hub, right? I want to say this. Other chains are trying to design shared security. They're saying shared security is part of our roadmap. This is like we're going to do that after the fact. Hopefully you've learned now in combination with my decisions of Polkadot why it doesn't work, why it doesn't make sense. That they're trying to add something after the fact, but they don't have these key building blocks. Now, maybe I don't know all of the different tricks in magic, but I think that if you are missing one of these building blocks, for example, if you're building an ecosystem without an execution meta protocol, or without coordination system, or without security hub, then you cannot provide shared security. That's my current understanding of the situation, right? So you need these mechanisms to provide it. Other people are going to market it, and it's going to be some lesser product. It's going to be something different. It's just marketing. So let's compare options. Let's look. So I was hopefully able to explain to you at a high level the parachains protocol, the Polkadot protocol. Okay. Let's look at the other ones. So as best as I understand, and actually I'm very open. If someone in this room knows more than I, let's have that conversation right now. That's great. But as far as I know, restaking solutions, the pros, they seem to be protocol agnostic and can be backported to new and existing chains. So that's really good. Like basically, if you didn't think about it before, you can create a restaking solution and just do it anywhere, right? You can use ETH token, restake it, and all that kind of stuff. So restaking. So the high level restaking is the idea that there is already a token out there which is valuable, like say ETH or Bitcoin. There is a way for you to bridge that token into my chain, which has low security, and then for you to basically do proof of stake on that expensive token, right? So you might not be saying, I don't, like, let's say there's a new chain, Shawn chain, and my token, my market cap is like 1 million, super small, right? You might not care about attacking Shawn chain if you lose Shawn tokens. But I could make a protocol which brings Bitcoin and ETH over hundreds of millions of dollars of tokens to my chain and use that in my security protocol, and I will slash your Bitcoin if you attack my chain. In this case, I'm able to take my small chain and actually increase economic security by restaking other chains. Now, there's a bunch of problems around this, which I talk about, but the idea is that smaller and newer chains can rely on more valuable and stable economies, right? That's the advantage of this. The cons. As tokens are continually restaked, the economic cost needed to attack a secure chain decreases. So if I use Bitcoin on 100 chains and try to restake all of them, then actually now I can make a coordinated attack to attack all 100 at one time and get, only partially hurt. Does that make sense? Like that the more you're reusing a token, the more you're splitting the value across multiple chains. So so it doesn't scale. There's no real computational verification or protection provided by these systems. So even though I have Bitcoin on my system, Bitcoin itself is not actually securing my chain. It's not actually bringing more security in terms of computational verification, right? It's just an economic side. And it seems to ultimately fall back onto centralized sources. So really to bridge things like Bitcoin over to my chain, often you rely on centralized bridges, centralized actors to bring those tokens over to my system. So often most restaking solutions are just reliant, like that restaking makes sense in terms of economies, but they're often reliant on middle actors, which are centralized, which then the whole house of cards crumbles. Yeah, Mike. So the question is, this can be decentralized. I mean, technology is possible to build. Oftentimes, these first mover advantages, like all these guys, they want to launch their product soon. What they do, they make a 3.5 multisig, and then they launch this thing. So often, most of these chains are not actually doing it well. And if they were going to do it well, why would you do restaking? You would just do a native protocol.
Can you explain point one again? Like, how is it? Like, is it just like a supply kind of thing?
So this first point.
Yeah.
So this first point is this: if I have $1 million of Bitcoin, and I restake it on one chain, if I attack that one chain, my $1 million is at stake. If I have $1 million of Bitcoin and I restake it on 5 chains, I now have 5 people I can attack, and I still only have $1 million Bitcoin at stake, right? So as you scale more and more, you could invent attack scenarios where you still have less proportionally at stake, and able to do more like more bad to the systems. Like I can attack 10 chains at once, and that kind of decreases my cost per network.
So basically, you're saying that like with restaking, you can take a million token X, and stake that same million across many different
chains. Exactly.
Okay. So
and now the cost to attack all of them is like 1/10. Like at a
so if you would like stake them across 1 million chains,
yeah,
then basically you have a what's the math here?
Like one Bitcoin at stake, whatever. But the idea is this: I'm thinking from perspective like a government. Imagine a government obtains a bunch of a token, and their job is one day to shut down all blockchains. Like their job is to like, I want to make sure this thing happens. They don't do it one by one. You know, you're just like squashing the Hydra. More heads will pop up. What they'll do is they will accumulate a bunch of stake, restake in all of them, and then attack all of them at once. You made the attack for governments resiliency now more easy. Again, it's a quite a specialized attack, but that's the idea.
In short, the main thing it does, it increases your risk exposure. It makes that the tokens you use they're like kind of on leverage, essentially. They're like, if you stake them in so many places at the same time, the risk exposure is significantly higher, because if any of them gets compromised or attacked, potentially a whole stake is getting slashed and putting all of those systems at risk.
Right. So you're thinking about the consumer perspective. I'm thinking about the attack perspective. Those are both valid points.
I think he's talking about liquid restaking, which is essentially leverage on top of leverage. I think, for example, these are essentially IOUs. So let's say that you stake DOT and then you get a receipt, right? That you just stake the DOT. You can go ahead and stake it in Shawn's chain, and Shawn can also give you another receipt, another IOU, and then you can go and stake it into, you know, Gavin's chain. And so you're literally getting leverage on top of leverage. And let's say that, you know, one domino down the line gets slashed, everything falls back. So you kind of get kind of that Luna Terra effect.
This is very much like, what would you design if you didn't think about this at all until now? Like literally, it's kind of very much after the fact. So it's not a great solution, in my opinion. If you want to learn more, I think the most popular restaking solution is Eigenlayer. Is that right? So I think that you would look in Eigenlayer and you can learn about what they're doing. And they might be doing some stuff that is cool, right? But this is just the pros and the cons. I'm just describing to you.
Eigenlayer is the main one in Ethereum, and it exactly has the same issue you just mentioned right now. It has this leverage problem that if you get slashed in one, you are compromising the safety of the whole Ethereum network, because you just staked your Ethereum in some other project on the side that was compromised.
Okay.
So just one more question. So the same thing, like when you mentioned restaking, you mean that the same 100 tokens will be used in the other places? Or because what I understood that only if you do it on 10, each one of them will have 10. But now we're discussing that
it depends on the protocol. It depends on the protocol. Restaking is a more broad idea. Restaking is the idea of moving other economies to your economy.
Yes.
The implementation detail is like protocol specific. Does that make sense? So you're asking me about something more specific than the idea.
No, I'm not. Okay, I understand. Okay, my question maybe was not the best, but if I have 100 and it's on 100 chains, it's still the 100, right? Even if I attacked the 100 chains.
Okay, 1 or 2 sentences. You can think of it as IOUs, okay? So let's say that I go ahead, okay, and stake, I'm gonna call it ETH, because that's the shitty one. Okay, so I stake ETH in Boda's chain. Okay, Boda is gonna give me an IOU, right? B ETH, let's call it that. Now anybody can go ahead and claim, actual ETH by going in there, right? But let's say that, we go to Juan's chain. Okay, now Juan says, or service maybe, you know what? I also accept B ETH, Boda ETH. Okay, so then someone else grabs it, stakes B ETH, and he issues, J ETH. Okay, so you're literally getting IOUs on top of IOUs and so forth. Now, if some service or chain down the line, happens to break or something happens to it, you see an entire domino effect, right? So it's like literally leverage.
Let's keep going, okay? Optimistic rollups, okay? So there's two kinds of rollups, optimistic ZK. Let's go optimistic first. So what are the pros of optimistic rollups as I understand? They're not limited by the complexity of the on-chain VM. All of this stuff is happening optimistically, it's happening off-chain and being reported optimistically. They can be parallelized, right? You can have basically many optimistic rollups running at the same time, propagating stuff. They can stuff a lot of data in their STF. Again, because the data is being, all of the computation of that blockchain is happening off the main network. You basically can stuff a bunch of data, run a bunch of stuff, do it in parallel, and you can use compiled code native to modern processors. These are all the aspects of optimistic rollups that are great. The concerns. There's concerns about centralization and censorship of sequencers. So sequencers are these things that are actually doing the roll or are constructing the rollup, running the blockchain. And there's concern around at that level, even though you're getting nice security from a chain like Ethereum, at that level there could be centralization risks, right? There could be there are, and this is probably the number one con of an optimistic rollup, long time to finality due to challenge periods. Because an optimistic rollup is all doing things optimistically. So basically, you have a sequencer, it makes a block, it reports it to the chain itself does not re-execute the block. It does not actually validate that block is valid. What it does is it waits for someone else, anyone else in the world, to challenge that block. That makes sense? This is why it's called optimistic. So again, in Polkadot, we validate every block is actually being executed correctly. Here, I report something, and it could be right, it could be wrong, but I put my money at stake for if that no one else will say that it's wrong. But because we need to wait for someone to say it's wrong, we can't just say, okay, we're gonna wait for 1 minute. You have to wait for, I think it's like 28 days or like 14 days, something like that. A long period of time. We cannot even finalize one block until that challenge period is over, right? So it's a very long time to finality. And of course, as you decrease the challenge period, you increase the ability to attack your network, right? You only need to fragment the network long enough for the challenge period to get by, right? Settlement layers could be attacked, interfering with the optimistic rollup protocols, right? So like, we've seen this before where Ethereum itself, during an NFT drop, is being very congested. And what happens to a layer 2 that's using Ethereum? It's stalled because it can't get its block into Ethereum. Not unless it pays a lot of money. And it suffers from the same problems of allocating block space as on-chain transactions. On-chain costs to perform the interactive protocol, so you have to basically scale that layer to handle all the transactions of submitting a proof, challenging the proof, doing all that process is just transactions on Ethereum. So if Ethereum costs are $100 per transaction, that entire process becomes $100 per block, right? And congestion of the network. So basically, you are limited to the scaling of that settlement layer. Zero knowledge rollups, okay? Honestly, they're pretty great. I think they're very exciting. Oh, you want to go back?
Yeah.
Go back.
Can you expand on this first pro, like not limited by the complexity of the on-chain VM? Because like when you invoke a challenge, the on-chain VM essentially executes the state transition.
My understanding is that's like maybe that's one implementation of optimistic rollup. But my understanding is optimistic rollup does not necessarily need that. What instead needs to happen is you could have optimistic rollup where let's say it's Ethereum is the main chain, and you have some like Shawn VM that someone submits the proof there, and then anyone can challenge it. That Ethereum chain at that point can have a protocol where basically validators inside of my Shawn chain need to vote on if it's good or not, right? That the Ethereum could be agnostic to the whole process. It's just like using some kind of like off-chain consensus to determine that validity. Now, it could also be if you have an EVM-based optimistic rollup, then you could then only run it when it needs to run, right? But at that point, you have limitations. For example, you cannot build a optimistic rollup which wants to have a bigger gas block than the Ethereum gas block, right? So there are ways to build kind of ones closer, But in general, and from my understanding, at the most high level optimistic rollup, it does not require that the VM is the same.
But in your case with your Shawn validators, and if you ask them what is like true and to invoke the challenge and everything, how is that inheriting security from Ethereum?
Because oh yeah, that's kind of a good point. I mean, in my high level answer is that you're basically you're basically making all those decisions on a network which can come to consensus. So it's like that process is also a decision process, and the consensus of the rules, like everyone submitting a proof, that's happening on a secure chain. Does that make sense? So like all of the steps of that process could be secure. But you're right, if you don't exactly re-execute the code, you're kind of not inheriting that security. Right, that's another bad reason for like again, what I'm saying, for me, what would be sexy about optimistic rollup is one that is not limited by the block size of Ethereum, right? So what you described here is maybe one that's more secure, but not then you might as well just do what we're doing with Polkadot, right? So yeah, one more question.
Just a slight comment. Yeah, you could have like different VMs. The sequencer will be the one that replays the transaction, so it'd be like a custom sequencer if it's a not EVM.
Yeah, but I think his point is that but no one on Ethereum shooting it. You're just so in that case, it's not like technically secure, but it's you know, the consensus about that message will be secured on a secure network. So high level. Okay. Again, what's hard about these things too is that it's hard for me to make a slide like this when there are many variants of optimistic rollups, right? So I can only talk about a high level. It could be that some protocol, the con doesn't apply or the pro doesn't apply, but this is the high level idea pictures, okay? Okay, zero knowledge rollup. So as I said, they are pretty cool. I think that ZK stuff is very new. Like the bulletproof paper only came out in like 2014. I don't know, like it's new stuff, man. And I think that, you know, I would not be surprised if the future of Polkadot and ZK proofs like intersected. I would not be surprised if there's some kind of way that we can use ZK stuff to make Polkadot better. There's already some of that, right? The ZK snarks is being used in Sassafras. So there's already some ways, but like maybe more to the validation, right? So they're very cool. What's very cool about them is they're proven trustlessly. Once you have a ZK proof that once you execute it, it's like there's no time to finality. It is like as soon as it executes, it is proven to be true, right? So it's like it is no time to finality at all. There's minimal data availability requirements. So, you know, because of the way the proofs work, like all this stuff is being like, you know, wrapped up into this one proof. The proof itself is like usually fixed size or small size. The data requirements for running that proof is really small. Instant finality, and it's not a meme, it is literally instant finality, right? And it's exciting if the future of recursive proofs work out. So the idea that you can have a proof inside of a proof inside of a proof, you check one thing and you're like, you know, validating, you know, a million blockchains at once. That's very cool ideas. The concerns, again, with ZK proofs, even more so, there's concerns around centralization of sequencers. Because in order to create a ZK proof, you need to do a lot of heavy work. The preparation of that proof is very, very heavy. So the kinds of nodes or computers that can actually run or generate those proofs for very scalable blockchains is very limited. It is very challenging to write ZK circuits, right? So they are Turing complete, but usually very computationally complex. And it's very hard to bound the complexity of the circuits when building apps. So there's all these layers in research right now happening to try to convert like Solidity contracts into ZK circuits, like, you know, in a instant way. But like the complexity and efficiency of those circuits is often very, very, very hard. Like if you want to build a really good circuit, you need to build it at the circuit level. You can't build that at like a high level programming language level, right? So often these programs that are like developer centric are not friendly or scalable. Maybe they're scalable. They're not today at the point which you want them for production use, essentially. I think that's the best way to say it. They suffer from the same problems again as allocating block space. So again, this goes back to the same slide as before, where if you're relying on Ethereum to be your ZK prover or like the ZK validator for the proofs, then you're still again relying on transaction fees of Ethereum, the block availability of Ethereum, the congestion of Ethereum to actually support anything. And again, the main thing is that Ethereum does not treat L2s as a native part of their protocol. And L2 is just another smart contract. CryptoKitties or your crypto zombies or whatever is using the same resources, the same level of priority as your ZK rollup. And in fact, probably using more priority because these guys, these degens are pumping up the fees to make sure that they get that trade in. Where your ZK network can't necessarily afford to pay thousands of dollars for every block it wants to validate, right? It's just not going to scale. So the fact that Ethereum does not have this kind of roll-up stuff as a native protocol, I think is very bearish. I think if Ethereum stepped up and said, hey, we are making L2s a part of the native protocol, I would be much more bullish. So finally, let's go to Polkadot native share security. And there are cons. There are cons to this process. And I've explained it hopefully as best as I can. The pros: you have protocol level handling of sharding, shared security, and interoperability, and data availability as well, right? It is easy to develop the state transition function. Anything that compiles to WASM, and compilation to WASM is actually very efficient nowadays. Like in Polkadot, when I first joined Polkadot, it was about a 10x performance. No, so it was a 100x performance decrease between native and WASM, and about a 10x decrease between native and the compiled WASM. I think now it's about 2x. 1 point something, even better. Like WASM has gone a very long way. It's easy to, you're writing Rust code, or you're writing C, or you're writing whatever language you want to compile to WASM, and you're actually getting very efficient WASM code out of it. It is probably the best time to finality, usually under a minute. So again, unlike an optimistic rollup, which needs a long time, we are actually on average, I think, finalizing a parachain block every 12 seconds. But even in the worst kind of congestion scenarios, we've seen mostly just under a minute. That's very nice time to finality still. Even better than Bitcoin is 10 minutes or so. We are actually getting all this parachain protocol to work within a minute. Data availability provided by the existing validators, so you get that for free. You don't have to build a secondary chain, a secondary token, a secondary economy, right? Secondary APIs, secondary bridges, like it's just built into the system. There's much less concern of centralization from collators versus sequencers and provers. So again, there are these things of collators. Collators are this thing that need to exist for parachains to exist, but the centralization risks of a collator is much, much less than the sequencers and provers inside of the other rollups. What are the cons? Okay, I told you I've been shilling Polkadot. What are the problems? And this is truthfully problems, right? There are unfortunately certain limitations enforced to keep the parachains compatible with the parachains protocol, right? So you need a WASM STF. You cannot build it in anything but WASM, right? If you want to use a library which isn't compatible with WASM, tough luck, right? It just doesn't work. There is no custom hosts function. So because every single parachain needs to execute on the relay chain, you can't add your own custom host function because then Polkadot can't validate it, right? So any kind of host function, like I want to have a special ZK executor, I want to have a special API access or whatever you can imagine, you need to basically push that all the way to the Polkadot protocol. It needs to go all the way to Polkadot relay chain for you to have your parachain support it, right? So this is bad. This is kind of sucks. And it's a constrained execution environment. As we talked about, there's limits in how big the POV size can be, how much time you have to execute blocks. There's all these limitations. On your own blockchain, you can define those limits. You can say, I want my blockchain to make a block every 10 minutes. I want my blockchain to make a block with this much size, etc., right? But in order to support the parachains protocol in the way we designed it, you must have your entire environment constrained to our maximum requirements, right? So it's not great for a super chain. We can only validate this. That being said, with the refactoring of core time and stuff like that, it is possible on a chain that has more execution requirements that you can get more cores and execute things in parallel. So you could actually run multiple cores at once. But this is still in progress. I'm not going to put it off the cons list until it works in production. I think that's fair for everyone, right? Let's talk about what we can do today. Okay, WASM is unfortunately 2x slower, I guess 1 point x slower, something, 1 point something than native compilation. It requires a lot of data being provided and available in the POV. So, that your POV blocks, you need to include all of the data that you're doing to validate. So, for example, if you're building a smart contracts chain and you have in your one block the execution of 100 smart contracts, in your POV, you need to include not only the data of the smart contracts, but the whole smart contract itself in the block. Does that make sense? Like, it's actually, in this context, there's a lot of systems I can imagine which won't scale very well into the POV size, right? I think those are some fair criticisms. Yeah, comments? This is my last slide, by the way, so questions. Comments? Any comments from you? Do you agree or disagree? Any other cons? He agrees. Polkadot is not perfect. But there's trade-offs, all trade-offs.
Question or comments? Just again about the WASM, just so I wrote it down. Like in an imaginary universe where everybody had the same operating system, then the WASM advantage is nullified.
Yeah, I think so.
Yeah.
At a high level, at the highest level, yes.
Yeah. Just
also, WASM is a secure sandbox. So it's not only like like you wouldn't feel safe downloading blobs from the internet and running on your computer. The fact that WASM is inside of the sandbox is also very
So
important.
kind of like Docker in that sense.
Yeah,
But
okay, in that context, yes.
all
So,
I'm
yeah.
saying is that it provides like a shared, agreed upon, and
Yes.
consistent execution environment.
And then again, once like for this, yes, and then one step even deeper is that in with the mindset of like clients and the mindset of Web3 scalability, WASM is also a web native execution format. So browsers support it, Mozilla supports it, Google supports it.
Yeah.
Like that's all the ideas of this, and hopefully RISC-V will be in a similar state too.
Okay.
Like I would say this, I would say RISC-V, even though all the technology about it is cool, if it's not adopted at the same level as WASM has been, it might not be the best choice because it doesn't have this like native web
Yeah.
utility.
Yeah. Like if you would just say, you all need to run on JVM or something. Then
Exactly.
yeah.
But so again, that doesn't apply to the idea of shared security, but applies to the other decisions and values of Polkadot, right?
Yeah.
Okay.
What is a theoretical limit on the number of parachains that the relay chain can support?
I can. You want to say a number? Then I have some ideas on things too. I was going to talk about the multi-scale. All right. So, I think that our goal is for a single relay chain to support up to 100, right? But 100 cores, not parachains, cores, right? And then on those 100 cores, you can have, thousands of different parachains running in these, fragments or small things or turning off, turning on, whatever. Now the question is, what if we need more cores? There is this idea that I heard about before, which was this like Polkadot squared or Polkadot cubed. I don't even know what they called it nowadays. But the idea is this: could we have multiple relay chains? They could all provide some level of cores, but in order to have shared security, you need to have a shared validator pool across these relay chains. So there could be 6 relay chains, but in order to have shared security, the same aspects, you need to have a single validator pool, which will then go across these different things. And so there are algorithms where you could basically take a validator pool of 10,000, turn it into 10 pools of 1,000, and then have 10 relay chains. And there's research, I think, published by the Web3 Foundation on this. And basically, you need to increase the assumptions around the number of honest validators. So in a single relay chain, we have the risk at 66% honest validators, something like that, right? In a nested chain where you have 10,000 here, you split into 10 groups, you need a requirement of 80% honest validators. So it increases some of the assumptions, but this is one way you could scale it. But for now, I think 100 cores. What we've seen in Polkadot is that we've made too many cores. Like if you look at the cost of the parachain auction on Kusama, you can buy a whole block space for a year for like under $100. So the limiting factor here is actually not number of cores. We have too much resource available. So we're not worried about it right now.
It's something like, I think I might have heard this. You said nested relay chains, right? Is that?
Yes.
Okay, I remember Rob mentioning that, I think.
Yeah, but the idea of nested relay chain has slightly evolved into this like into bridge relay chains.
Bridge relay chain.
But again, this is again a problem that's actually not top of mind right now. It is not actually a scalability issue today about how much block space we're providing. We're providing a ton of block space. We don't have enough good users for it, which I hope that you all will start using it.
Yeah, to follow up on that. So generally speaking, right now we have 300 validators in Polkadot. We can get up to 1,000, but we never ever want to go above 1,000 because then our networking just starts collapsing. So 1K is pretty much the limit for validators. And the core of the question, you were asking about parachains, but you should be asking about cores. I think Shawn alluded to that because the cores is the actual thing that like creates block space for us and creates core time, which actually computes all the transactions. If it's like a few parachains, a para-thread, or like on demand, it doesn't really matter. The core is the unit you're asking about. And when it comes to cores, we generally right now have 5 validators per core. We can drop it down to 3, and we might drop it soon, but we want to maintain something between 3 and 5. So if we go up to 1,000 validators, 3 validators per core, this gives you a rough estimate of how many cores we can have on a single relay chain. And then we have this whole idea of potentially having more relay chains, but we are so far away from even needing that it's just a very far away theoretical discussion later down the line. It might be a bit more realistic once we have elastic scaling, so having multiple parachains, having the same parachain on multiple cores, then we might have like a big parachain consuming a few cores. So then having more cores might be beneficial, but for now, it's not necessary at all.
If you buy him lunch, he'll talk to you.
Yeah, let's do it. Let's go lunch. Thanks.
decentralization, in one of the previous slides you mentioned trusted validator for the relay chain. Can you elaborate a little bit more? Yeah, this one.
I don't think I ever said there's trusted validators.
Yes, a few trusted validator.
Maybe maybe this slide. There's some. Well, it's not highlighted. We want to minimize trust. So what do? So in this process, we have a bunch of validators, but we don't want all of them to execute everything. If all of them were executing everything, we wouldn't scale. It wouldn't be sharding, right? So we want some of them to execute some of them, right? Like some of the parachains. But we want a process so that if needed, if something is happening within the smaller group, that we can escalate to the whole ecosystem. So I guess maybe what you heard from me or something I'm saying that I said was that basically you choose which validators are executing which parachain block, right? And then if they can't come to consensus, then things escalate through the disputes process or through the approval checking to actually escalate to more and more validators until basically everyone in the whole chain is running the block. And again, we assume for this system to work, we assume Polkadot is secure, right? So if Polkadot itself has a Byzantine fault tolerance problem, the parachains will have a Byzantine fault tolerance problem. But we're assuming to start with that Polkadot is secure in a blockchain, like it has 20 billions of security backing it. You know, we have this whole process of how blockchains work. And if that's the case, it can provide that same security to the parachains.
Okay, I thought there were some special validator for the relay chain.
No, unlike other protocols,
that was
our validators are just general, you know, like
all of them are equal.
All of them are equal in power,
Yeah,
exactly.
Yeah.
Exactly. We do not have
tricky validation.
We do not have these bullshit, you know, special nodes and then say we're decentralized in other ways. Yeah. Any other questions? You guys have a feeling now. Okay, I just gave two presentations. First presentation, philosophies, right? I think very much that leads into the decisions here. And you have the idea now that with all of this in mind from day zero, the decision to build shared security is extremely important. If there are protocols out there which are designing it today and they already launched a token, that's like red flags, man. Like this was built in and designed from the protocol. And you can see how low level, the decision to use WASM, how important it was to be the backbone for a scalable protocol on doing shared security, right? And how important this resource is for a multi-chain future. So I hope you have a high level understanding now of not only Polkadot, but shared security and how it applies, you know, kind of in our ecosystem, how it works at a high level. And again, the low level details, exactly how you prevent all these stuff, you'll get presentations on that throughout the week.